Hello, everyone. Thank you for coming to this talk. I am Dev, and I'm a dev. I've been building full-stack JavaScript applications for about 8 to 9 years. This is my third year speaking at Star Trek. So before we start, can we quickly give a big round of applause for the people that put this event together and maintain this entire community? Thank you. So I work as a developer relations engineer for PowerSync. We are one of the sponsors for this conference. We have our booth outside, so please come and visit. And also, this is a sponsored session. I am on the core team of Solid.js, which is a JavaScript UI framework similar to React. I also make content on YouTube, and I'm kind of terminally online on X. So you can follow me there if you have any follow-up questions, or you can just stop me in the hallway. So this talk is called Building Fast, Real-Time, and Offline-First Applications. Let me quickly define those terms so that we have some clarity on what they mean in the context of this talk. Fast means that we want to build apps that respond or react instantly to any user interaction or user feedback, which means when a user does something on your app, the app should immediately show some feedback instead of getting them stuck on a loading spinner and having them wait for things to settle. Real time means that if you're looking at some piece of data, or if a user is looking at some piece of data that gets changed by someone else, that change should show up on the user's application or the user's device automatically without hitting the refresh button and as fast as possible so the user doesn't look at stale data for too long. And offline first means that if the user's device is offline or in a spotty, unreliable network, the app should continue to function as expected rather than degrading in performance. Now, I don't want to bore you with words too much, so we're going to immediately jump into a demo. This is the kind of experience that users expect. Let me go back to the online here. So this is a very simple, I have it in 2 different tabs, but this is a very simple Kanban board, Kanban application, where you can create cards like this. You can see that these interactions are instantaneous. We can move them on the board as well. And while we have a busy indicator that shows that things are being synced in the background, all the interactions themselves are instantaneous, which means the user is free to add a card and then immediately go and add other things. This is the kind of UI that builds trust with the users, because things kind of only happen when the user is expecting them to. All the changes, all the feedback is visible instantaneously, deletes as well. And things mostly happen in real time. So if I go here, and if I move this card back to the to-do column, we see that the same change reflects on both tabs after a while, but it happens as quickly as possible. So if I close this one, or if I delete that one, looks like their demo gods are not with me today. But at the same time, if I'll bring these both back online. And if I go on offline in one of them, I'm still allowed to make changes and add more cards. And when I come back online, things should just kind of sync with the server as expected. But that's not the kind of apps that we usually ship. What are the experiences that we actually ship to our users? Well, first they look like this, where the user is stuck on looking at a loading screen or a loading spinner and waiting for things to load. And when they do see the application, they can make some changes, but they have to wait for a while for their changes to actually show up, because the application waits for the server to acknowledge what they just did. This also makes making changes more difficult, because things can happen kind of after the user has already interacted, which is what we call a jank UI, where things kind of just move around or appear to move around on their own. And this is the kind of experience that loses trust with users, because when I click here and I move my mouse down here, I might accidentally click the wrong thing, because by the time I click it, the UI has moved from under my cursor. This forces the user to wait for the UI to settle before they are allowed to do further things. This is the kind of user interface that blocks the user instead of enabling them to be more productive. And obviously, none of the changes show up on the other side of the board until you manually hit refresh. And if we go offline, this is going to almost certainly break entirely, and it's not going to even load the data, much less allow the user to change the data. So from the outside, it makes sense that the kind of apps that we should be shipping should look more like the first demo, which is instant and real-time and offline first, rather than this second version, which seems to be broken. When a user runs into these edge cases, they simply assume that the app is broken. But if we jump into the code for these two demos, it's going to become very obvious why we don't ship the first experience. OK, so this is the code for the second demo, the one that's slow and has these issues. It's going to look pretty standard. We have our state. We have some state for. Let me zoom in. Get rid of that. OK, so this is a simple React component. We have some state for our columns and cards. We have some busy state. We fetch some sort of we interact with some sort of an API to fetch data and update our state so that this state can be rendered on the UI. We fetch our data when the component is first rendered. And when there's any user events or user interaction, we set our busy state. We hit our API again to make the mutation. And we call refetch so that we can fetch a fresh version of the data and update our state with it. This is the kind of logic that's easy to write, easy to reason about, both for us and our AIs. But we see that this is not going to result in the most optimal user experience. So what does it look like if we try to make our apps fast in real time and offline first? Well, the first thing is that they're going to be much more complicated. So if we go back to our basic version, we can see that the other version here is almost 3 times as much code. And the reason for that is there is a lot more going on in this version. Well, for starters, we need to establish a real-time subscription with the server so that we can get updates in real time. And we need to keep track of what mutations or what interactions the user has applied so that we can apply them locally first, which we call optimistic UI. But these two things don't interact well with each other, because when you have local optimistic changes, you can't simply apply the changes that you're getting from the server in real time. You need to defer updating that state until all the local mutations have been resolved, because any server-side update is going to override any local optimistic changes that your user might have made. There's also a layer of offline data here. The first time you open this app, it retrieves data from a local offline database, and all the changes need to be tracked in the local database, as well as any mutations that have been made while offline. When the user is offline, we need to track the actions that they have made separately so that we can replay them once the user comes back online. We also need to obviously keep track of the actual offline and online state. And we need to keep track of how many operations are pending so that we can show a busy indicator. Trust me, I've only started digging into. I've only explored the surface of what all this code does, and I don't mean to show all of this complexity to discourage you from building this in your apps. In fact, this is a great way to learn how distributed systems work, which I'll come back to in a second. The more important point here is that is this sort of code ever going to be something that we want to write and maintain at our day jobs? Is all of this code ever getting prioritized over building features or fixing bugs from our backlogs? And is AI ever going to be able to reason about this code and maintain it for any sort of a reasonable capacity? Because the truth is, this code ultimately is what we want to write because we want to keep things simple and maintainable. The end result is that we have to pick between this trade-off of keeping our code bases simple and maintainable over time at the cost of having a bad user experience, versus we build a really good user experience that works like how users expect it to, at the cost of making our code base super complicated and not maintainable. The problem here is that the fundamental architecture of how we build these apps and how we think about these apps is broken. And the reason is that full stack apps are distributed systems. We have state on the server, and we have state on the client. And keeping these two pieces of state in sync with each other is a very difficult distributed systems problem. It's not impossible. I built this simple version, or I built this version in a couple hours. Some of you can probably do it much faster than me. And you can probably spend a weekend to make it completely bulletproof. Because even in this version, this Kanban board is a very simple app with a very simple data model. Any applications that we get paid to work on are ultimately going to have a lot more complexity in data structures and in the user interaction model, which means all of this code is going to get infinitely more complicated. At the same time, there's a lot of edge cases and race conditions that I'm sure I have not even thought about, and I haven't even started thinking about how to make this efficient. So again, this is a lot of complexity, which you are free. I encourage you to go and try to build this, but we probably don't want to do this in our day jobs because we also have to find ways to scale that across our code bases and across our teams. So what I'm proposing is that we use a different architecture to think about these sort of apps. And this is what sync engines like PowerSync offer. What if your client or your front end simply interacted with a local database like SQLite, and a sync engine like PowerSync was responsible for keeping the data between your local database and your server-side database in sync? We can write reactive queries against our local database so that our UI immediately updates on any changes. We can also have all our mutations happen locally first so that those changes are reflected instantly everywhere. And we also have offline caching so that the users can continue to work if the device has bad network or no network. Let's see what that looks like. I have another demo here. I don't have two tabs anymore. And you're going to see that it feels very similar to our first demo, which was fast and real-time and offline first. So there's actually not too many interesting things to see here, because the more interesting part is the code behind this demo. The first thing we will notice here is that our state comes from these simple SQL queries that are made against our local SQLite database. Whenever any data in these columns table or in this cards table changes, these queries are going to automatically rerun, give us the updated data, which will re-render our component and show the new state in our UI. The events are simple as well, where we simply need to run insert, update, or delete queries against our local database. And the end result is that this code is not only simpler than our complicated version that had better user experience at about 375 lines, but this code is also simpler than our simplest broken version, which is at about 128 lines. And the reason is that through the power of reactive queries, or queries that rerun automatically, we are able to eliminate any refetching and revalidation logic that we might have in our UI. So in here, we can see that, and at the same time, we get rid of tracking busy states manually. So you can see here that for adding a card, we need to enable a busy state. We have our actual mutation against our API, and then we have a refetch. But in the PowerSync version, we simply insert that card into our local SQLite database, and that's it. PowerSync ensures that all the relevant queries will rerun and update the UI. At the same time, it'll make sure that this change goes to your backend and your actual database, and it also gets streamed to all the other clients that might be looking at the same board. And it also makes sure that if you are offline, this change is not only made against the local database, but it is queued offline so that it can be synced with the server once you do reconnect. So overall, that maybe sounds too good to be true, that you just write simple SQL queries directly in your UI components against a local database, and everything just works. Well, Kind of. There's obviously a little more going on, because in any sort of real application, you would have validation and business logic, authorization, and potentially some conflict resolution, and those sort of logic cannot live on the client. They need to live on a backend or on a server. So let's look at what else is needed here to make this function. The first thing we'll see here is that we are creating a client-side SQLite database, which we are storing in this file here. The most important thing is a schema. The client-side database has its own schema, which is how we write our local read and write queries. However, this schema can be changed without needing to write migrations for the local database, which means when your schema changes on the backend, you only need to write migrations for your backend data, and for your client side, you can just change the schema and deploy a new version, and everything works. This schema can also be auto-generated from your server-side schema. And the second thing to note here is the connector. This connector is how PowerSync integrates with your existing backend and auth. The first function here gives PowerSync some auth context. So for example, a user ID or a user role, which we'll come back to in a second. The second function here determines how your backend processes the changes or the mutations that have been made locally. Because we don't want to simply allow the client to make any random mutations and have that be replicated on the server, this function basically gives you a list of all the changes, all the transactions that have been made locally, so that you can upload them to your own backend API endpoint. And that's where you would apply validation, authorization, business logic, and you would determine how these changes should be made to your backend source database. If you decide to reject a mutation or to apply a mutation differently, that is considered the source of truth, and it's going to override any changes that have been made locally. So this is a server authoritative system. Finally, there's also this piece called as sync streams. So we don't want to synchronize the entire backend database with all your user or with all your client databases. We only want to synchronize the subset of the data that is relevant to that user and at any given point in time. Sync streams are a way for you to decide what data gets, or what partial subset of the data gets synced. Now, I just happen to be synchronizing everything that's in my columns and cards table, but this is where the auth context comes in. This is where you can use the user ID or the user role provided by the backend connector, and you can determine exactly what subset, and you can apply filters to this data. We can also pass in dynamic parameters from the client, so you can determine what data to be synced depending on, let's say, what page the user is on. So overall, the combination of sync streams, the backend connector, and the schema itself gives you a great deal of control over what data gets synced and how, so that ultimately your front-end logic can be as simple as this, where you simply make reactive queries against a database, and you mutate things in the database directly, and everything gets synced automatically. If you're building AI apps, this is actually a bigger problem. And that's because when you're integrating AI or LLMs into your application, you might have it a simple HTTP stream or a server-sent event stream from a client that transports all the LLM token or LLM responses back to your client. This is actually a very dangerous approach, because client-server connections tend to be fragile, and if anything here breaks, the LLM response is kind of just going to be lost, and it's very difficult to recover that, and you probably have to start from scratch. At the same time, there's a lot of complicated logic that you have to implement both on the server side and the client side for handling these special streams and long-running streams. And at the same time, you still need logic to persist these responses in your database, and your client needs additional logic for any refetch or resync from the database on demand. This overall makes building AI-powered front ends really complicated. And if you have tried to make an AI-powered interface, you probably know that making them reliable is very, very difficult. You can probably also see the pattern at this point, but spoiler alert, you can eliminate a lot of your code complexity. At the same time, you can have a much better user experience if you use a sync engine here, because a sync engine allows you to simply take these AI responses and write them to your database without any other effort. The sync engine will be responsible for taking these responses from your database and syncing them to the clients in real time. This means not only that you eliminate all the stream handling logic on your client and the server, but your client gets to stay as simple and dumb because there's no additional logic other than reactive queries against the database, which you already have. This also makes it much easier to have multi-device and multiplayer support for AI without any additional effort. So that's my talk. Please visit powersync.com if you want more information. I have a lot of blog posts, both around the sync engines in general and their UX and DX benefits, and also some blog posts specifically around AI applications and how you can level up your applications using a sync engine. This is something that we call the network tar pit. Thank you for coming to my talk, and feel free to ask any questions. Thank you very much.